Thank you, Michel, Gustavo. I'm going to talk about biomolecular synthesis again, but from a quantum chemical perspective. So we all first let me acknowledge my collaborators, my theoretical collaborators here, Dr. Tim Lee, Professor Martin Head-Gordon, Professor Thomas Stein, and my collaborators at NASA Ames experimental side, Dr. Scott Sanford, Michel Nuevo, and Chris Mataris, and funding from NASA Astrobiology Institute as well. So we all know by now that that biomolecules or organic molecules are formed on the surfaces of or found in the surfaces of meteorites and bodies that are extraterrestrial in origin. We stick to answering questions of how they are formed and why they are formed, and by which processes. So here is a cartoon of maybe molecular synthesis in the gas phase, which may then be incorporated into parent bodies, such as grains. Or it could be formed on the surface of the grains or on the surfaces of the grains that is covered with a little bit of ice. And we know these molecules can be as complex as sugars, nucleobases, alcohols, etc. We try to look at what physical processes that create the reactants, what reactions are possible, what's not possible, what products are more likely to happen, what is less likely to happen. So this is again in sort of motivated by and in collaboration with experiments where Michel, Chris, and Scott has done this, and many others have done this. That looked at ices in the laboratory and then exposed the ices with UV light and seen organic molecules forming. And here they have mixed purine with ammonia water at low temperature, deposited on an aluminum foil, ionized with or irradiated with UV lamp, and experimented with HPLC and GCMS, and found all sorts of interesting molecules, including hypoxanthine, adenine, guanine, isoguanine, xanthine, and so on. And so we try to understand what might have happened in between depositing and identifying the molecules. So what might have happened was you have about 10.25 electron volts of energy that may break water into hydroxyl, may break ammonia into amino group. It does not ionize water because 12.6 electron volt is not available, but it can ionize ammonia, it can break ammonia, and it can even ionize and break purine into their components. So all these reactants are available in this system, except for H2O radical cation. They then go on to react in various ways. So here is just a few of those, and we look at each one of these, but I'm going to point out just a couple of them. So here is neutral purine reacting with water or ammonia, neutral purine reacting with hydroxyl or ammonium, amino group, a radical reacting with a radical cation of purine reacting with hydroxyl or amino group, and so on. So I'm going to stick to this, and for a good reason, which will be clear later, stick to reactions between purine cation and hydroxyl and amino radicals. These are radical reactions, so easier, but there's a good reason for it. But all these reactions we have actually explored, and it's available in our papers. You can always go and look at those. We use primarily for this work density functional theory, using one of the most modern density functionals called omega B97M-V, along with a large enough basis set. And for condensed phase calculations, we do a conductor-like polarized continuum model. So these are two sets of calculations between gas phase and explicitly condensed phase calculations. And sometimes we use molar placid perturbation theory as well, depending on the need. So what we really do, we try to explore the mechanism of these reactions. So here is purine cation for you, reacting with a hydroxyl radical, giving you an intermediate that needs to then lose a proton to give you the product. The product in this case is 2-hydroxypurine. It can happen in a different way as well. Purine cation reacting with water give you in between a few steps, giving you the same thing. And those same reactions can even happen with amino group and many other reactants. So if we look at each one of these reactions, let's look at the amino reaction first. Here's a reaction diagram. So the x-axis is your reaction coordinate, unitless, and y-axis is energy in kilocalories per mole. Here's the reactants. You have the purine cation, the amino group, and the water, and the intermediates here and the products there. Now the intermediates form in this case without any barrier because you have a reaction between a radical and a radical, and that gives you the covalent bond formation here. But these molecules still need to lose a proton, and that proton is lost because of the water around it. The water's proton affinity actually pulls the proton out and gives you these products. If you didn't include this water in this equation, these energies for the products would be somewhere around here, which means the reactions will not be favorable. You need to include at least one water, actually more than one water. But in this case, even with one water, the reaction energies become favorable. This already tells you that pure gas phase reaction is kind of difficult. Pure gas phase reaction between this radical cation and a radical will give you the intermediate, but not the products, because the proton's still going to be stuck there, and you need something to pull that proton out. Water does that right here. You can show this using condensed phase calculations explicitly here. So these are CPCM calculations, and again, we make the reactants zero arbitrarily and see what happens to intermediates and products. Here you see that the effect of the condensed phase clearly. It pulls the energies down farther and makes the reaction go better. Similar things you can now start. Now the other point I want to make from this is that you have two products, that is 6-aminopurine and 2-aminopurine. That is the most likely, what's most stable products. In this 6-aminopurine is nothing but adenine. So adenine is your most favorable product. If you take one of these two and or both and do the next step, that is an addition of either a amino group or a hydroxyl group, you would find something like this. So here's an example of adenine reacting with hydroxyl, and you have the reactants there, intermediates and products here. So if you start from adenine, you get to isoguanine. If you start from 2-aminopurine, you get to guanine. Here's guanine. And again, you see the same thing happening. This is a pure gas phase calculation in black and blue. You see the reactants, the intermediates forming, the products forming. The intermediates are still a little bit lower in energy, so that the reaction shouldn't go. But if you actually include the condensed phase, and the condensed phase calculations clearly show that the reactions go in the product's direction. So you need the matrix, you need the water matrix. These reactions do not go in the gas phase. So pure gas phase formation, oxidation or amination of purines to adenine or guanine is unlikely, but condensed phase, a surface covered with ice phase followed by ionization formation is very likely. So you may ask why I work with cation all the time. So here's the purine cation, and we've seen purine cations before. There's a good reason for it now, and it became clear later. So here's an example of that arrow is out of place. Here's an example of an experiment that Chris and Michelle did, where they deposited. How much time do I have?
2 minutes.
Okay.
2 minutes for questions.
Okay. So purine in pure ammonia and ionized followed by radiation, and we did the calculations and showed that you should be able to make adenine from it, because NH3 has strong enough proton affinity to pull that proton out. So you should get adenine and all other aminopurine products, except when they do the experiments, they don't see any. Now, this is an interesting case. It became clearer later when we found this paper by Quill et al., where they make this observation that the ice matrix acts as an electronic solid-state switch, where the relative amount of water and ammonia determines whether the positively or the negatively charged pH in this case, but in our case, purine, is formed. So in pure water, you have cations, and in pure ammonia, you have anions produced. That's because of the low ionization energy of ammonia and high ionization energy of water. Low ionization energy of ammonia makes ammonia cation plus an electron. Electron is captured by the purine or the pH, and you have the anion. So when you have the anion, the reactions don't go like the way I showed, and you don't see any product. That kind of proves the cationic mechanism, because the moment you have the water helps create the cations of the purine or the pyrimidine or whatever you are working with, and the cationic reaction goes forward. This is kind of the proof of the cationic mechanism. That's why I chose the cationic mechanism of all the mechanisms here. So now going forward, we just can do the same experiment in reverse. You say, how about the hydroxyl? If the hydroxyl attaches first, you see the same thing. In this case, you would see hypoxanthine instead of aminopurines. And then those can then take an H amino group later, and it will give you the similar products, basically guanine, isoguanine, and see similar ordering of energy. But now what is available will be important at the first step. So if you started from purine, if your first step was an amino group addition, then you expect to find adenine. If your first step was a hydroxyl group addition, you would expect to make hypoxanthine. This actually makes a very interesting case. If water is more abundant, so if you make hypoxanthine, you expect that in the next step, if it is an amination, then you would expect to form guanine. And if it is a hydroxylation, then you expect to form xanthine. On the other hand, if your first step was an amination, then you make adenine, and then the next step would takes you to isoguanine. All these products are possible. It just depends on what is available at the near environment and what reaction is statistically more feasible. So with all this, I'm just going to skip next few slides and come to my broad conclusions. Is that the cationic mechanism is likely the way these reactions go. It needs the presence of the water matrix for two reasons. Water actually plays the devil and the do-gooder. Here is a catalyst because it helps create the cations. It provides a matrix for the reaction, and also provides the hydroxyl radicals for the reaction. So provides the reactants too. But it also acts as a competitor, because once the hydroxyl is produced, it attacks everything, and the amino group does not have the opportunity to react. So it's sort of a catalyst and a competitor. And from our other experiments, we found that the uracil, adenine, and guanine are kind of easily formed, but thymine is not so easily formed, and that's the part I skipped. But you can always go back and read the papers, previous papers, which is kind of goes along with the absence of thymine in the meteoritic samples thus far. So with that, I'm just going to skip next few slides and come to and say thank you and take any questions you may have. Thanks.